Welcome to this HP Expert 1 presentation. In this video we're going to look at binary. I'd like to explain how binary works. I'd like to show you some tricks relating to binary and IP addresses. So for example, how to convert a dotted decimal IP address to binary and back again. Binary is a basic building block in networking, and it's really important that you understand how binary works. You'll encounter binary over and over again throughout your networking career. So in this video we're going to cover the reasons behind you learning binary, and I've already mentioned a few good reasons. I'd like to give you an overview and explain the basics of binary. And lastly, I'm going to show you how to convert an IP address in dotted decimal notation to binary and translate it back again. This is very similar to translating from one language into another. So for example, translating English to French. In this case, we're taking a dotted decimal notation IP address and converting it to binary format and back again. Let's get started. Binary is of great importance once again in networking. You're going to encounter binary when doing IP subnetting, for example, or when using access lists to permit or deny traffic. You cannot be a good network engineer if you don't understand IP addressing and subnetting, and thus a knowledge of binary is required, as you may use it again and again. For example, you might have a subnet of 10.1.1.0/24, and you may need to subnet that to 10.110/28. Without a good understanding of binary, that can be difficult. With access lists, for example, you can use inverse masks. So 0.0.0.255 is the inverse of 255.255.255.0. Once again, without a fundamental understanding of binary, it can be very difficult to do both subnetting and access lists and various other tasks in networking. All computers function by using a system of switches that can be either on or off. An off value is denoted as a 0 and an on value is denoted as a 1. So binary is a really simple language to understand. It has two options or two values, a 0 or a 1. Decimal, for instance, has values 0 to 9, but in binary it's always either a 0 or a 1. There are only two values that you need to understand. I wish learning a foreign language was as simple as this language only contains two words or values, 0 or 1. These values will be used in combinations, but essentially everything in binary boils down to either a 0 or a 1. As an example, 128 in decimal equals 1 followed by 7 zeros in binary. And I'm going to explain this in a moment. But notice either a 1 or a 0. Now to help you understand binary, let's use the following analogy. Imagine a cable. That cable can either have current or no current. So when there's current, that means 1, and when there's no current, that means 0. So a single cable can be in one of two states. It can either have current or not have current. When current is applied, the value would be 1. When no current is applied, the value would be 0. So a single cable, when there's no current, equates to a 0, and when there's current, it equates to a 1. This cable can be in one of two states. It can have current or not have current, and that gives us two combinations or two options, either a 0 or a 1. 0 meaning no current, 1 meaning current. Now continuing with that analogy, imagine you had two cables. Two cables can either have no current applied, so no current means 0, 0, or you could, for example, have no current on the first cable and current on the second cable. That would imply 0, 1. Once again, no current equates to 0, current equates to 1. And continuing with that example, we could have current on the first cable and no current on the second cable. That gives us a value of 1, 0. Or we could have current on both cables. So current on cable 1, current on cable 2, that gives us a value of 1, 1. So in this case, we had two cables but there are 4 combinations or 4 options. 0, 0, no current, or 0, 1, no current, or 1, 0, current, no current, or current, in other words 1, 1. The reason for this is that we have 2 cables and 2 possible states, either off or on. So 2 cables with 2 possible states gives us a value of 4. 2 to the power of 2 equals 4. Or if you prefer, 2 times 2 equals 4. So just to summarize, in this example we had 2 cables and 2 states per cable. 2 cables times 2 states equals 4 combinations. Thus 2 times 2 equals 4, or 2 to the power of 2 equals 4. So extending that analogy to 8 cables. The reason why is that an IP version 4 address consists of 4 octets or 4 8-bit values. In this case, we might have no current on the first 7 cables and current on the last cable. That gives us 7 binary zeros and a binary 1. We could once again go through the various combinations as per the previous examples, where we put current on the last cable, as in this example, or current on the second last cable, and then go through all the combinations until we reach a situation where we have current on all cables. If you went through all those combinations, you would end up having 256 combinations or 256 binary values. 2 states across 8 cables gives you 256. Now for the sake of time, we're not going to do that here. But if you decided to work it out, you would see that you get 256 binary combinations. So let's do a quick comparison between decimal and binary systems. Decimal is based on a 10 base system, where we have values from 0 to 9. This is the numbering system used in everyday math or maths, whichever term you prefer. Binary, however, is a base 2 system, which is the foundation of computer operations. Once again, we have 2 values, either binary 0 or binary 1. This is once again what we're going to concentrate on throughout the rest of this video. So all examples are using a combination of zeros and ones. Here's some basic math for those of you who might have forgotten. 2 to the power of 0 equals 1. 2 to the power of 1, which in other words is 2 multiplied together 1 time, in other words 2 times 1 equals 2. Extending that, 2 to the power of 2, which is 2 multiplied by 2, equals 4. 2 to the power of 3, which is 2 multiplied together 3 times, in other words 2 times 2 times 2 equals 8. 2 to the power of 4, which once again is 2 times 2 times 2 times 2, or 2 multiplied together 4 times, equals 16. Continuing, 2 to the power of 5 equals 32, 2 to the power of 6 equals 64, 2 to the power of 7 equals 128, 2 to the power of 8 equals 256. So some basic math. Essentially, 2 to the power of a value is that value multiplied by itself, in this case 2, multiplied 8 times, which gives you 256. This kind of basic math is really important when working with binary, IP addressing and subnetting. Now if you're ever going to learn a table to help you with binary and subnetting, this would be it. In the real world, we typically use calculators, but it's well worth knowing how to do this manually to help you with your understanding. So if you ever need to do this manually, I'd suggest that you write down this table, because it'll make your life a lot easier when working out binary to decimal and decimal to binary calculations. What you have in this table is firstly your base exponent. So 2 to the power of 7, 2 to the power of 6, 2 to the power of 5, all the way down to 2 to the power of 0. Put binary ones below that and then the decimal equivalent. So 2 to the power of 7 is 128. 2 to the power of 6 is 64. 2 to the power of 5 is 32. 2 to the power of 4 is 16, 2 to the power of 3 is 8, 2 to the power of 2 is 4, 2 to the power of 1 is 2, and 2 to the power of 0 is 1. These values are really important in IP version 4, so it's well worth remembering this table. Now imagine once again that we have 8 cables and there's current on every cable. So current on the first cable, second one, and so forth and so on. Current on every cable. That means that this value is 128, 64, and so forth. If you add all of those values together, so 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, you get a value of 255. Thus, 8 binary ones equates to 255 in decimal. That's because every logical cable is set on, in other words, has a value of 1, and this value, for example, represents 2 to the power of 5, which is equal to 32 in decimal. Adding those values together gives you the value of 255. So let's demonstrate this by using a Windows calculator. So in this example, I'm using Windows 7. I'm going to go to the calculator and change it to Programmer. That allows me to see, for example, decimal and binary values. So 255 in decimal is equivalent to 8 binary ones. Or once again, 8 binary ones is equivalent to 255 in decimal. 255 in decimal is equivalent to 8 binary ones. So here's another example. What is the binary equivalent of 1 in decimal? So using our table, the decimal value is 1. That means these values are turned off. In other words, the binary equivalent is 0 for the first 7 values, but the last value is turned on. So 1 in decimal is equivalent to 7 binary zeros followed by a binary 1. Once again, using our Windows calculator, 1 in decimal is equivalent to 1 in binary, but because we're using this mainly with IP addressing, you would tend to write it as follows. The Windows calculator removes the leading zeros. So 1 in decimal is equivalent to 1 in binary. In this example, what is the equivalent of 192 in decimal? So using our table, 192 is equivalent to 128 plus 64, which implies that the first bit is on, the second bit is on, and the remaining bits are set to 0. 128 plus 64 equals 192, thus 11 followed by 6 binary zeros is equal to 192 in decimal. Windows calculator once again, 192 in decimal equals 11 followed by 6 zeros in binary, equivalent of 192 in decimal. Here's another example. What is the binary equivalent of 253 in decimal? Now 253 in decimal is 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 1. That gives you 253. So 128 means the first or most significant bit is set on. 64 implies the second bit is on. 32, the third bit is on. 16, the fourth bit is on. 8, the fifth bit is on. 4, the sixth bit is on. And 1, the last or least significant bit is on. 2 is set off in this example. So 253 in decimal is equal to 6 binary ones followed by a binary 0 followed by a binary 1. 253 is equal to 6 binary ones followed by a 0 followed by a 1. So I'm hoping at this point you have a good understanding of how to convert decimal to binary and back again. There are many tricks with regards to binary that can allow you to speed up calculations. One example would be that 255 less 2 gives you 253. In other words, this value is set off, which will allow you to work out that 255 looks like this, but that bit is set off So 253 looks like this. Use whichever method is most logical to yourself. Once again, many people have different methods to speed up calculations. Now let's extend our discussion to IP addresses. IPv4 addresses are used to uniquely identify devices in an IP network. IPv4 addresses are 4 octets in length, in other words, 4 times 8 bits. Each octet is 8 bits in length, in the range 0 to 255. Just imagine that a bit is a logical cable that can have current or no current. In other videos, I'm going to explain a lot more about IP addressing and subnetting, but for now just understand that an IP address is 4 octets, in other words 4 times 8 bits. IPv4 addresses can be represented in both binary and decimal format. So here's an example, 10.1.23.19 is the decimal representation of an IP address. That can be represented as follows. 4 binary zeros followed by 1010 is the binary equivalent of decimal 10. 7 zeros followed by a 1 is the binary equivalent of decimal 1. 3 zeros, 10111 is the binary equivalent of 23, and 3 zeros, 10011 is the binary equivalent of 19. This is like saying tomato, tomato, or router. Use the term that you prefer. For networking, it's important that you know both, decimal and binary. So let's start with 10. 8 plus 2 equals 10. In other words, this bit is on and this bit is on. The other bits are set off. 8 plus 2 equals 10. Thus, 4 binary zeros, 1010 is the equivalent of 10 in decimal. 8 plus 2 equals 10. 8 plus 2 is 10. Other bits are set off. Only those 2 bits are on. What about 129? 128 plus 1 equals 129. This bit and this bit are set on. Other bits are off. Thus, 1 followed by 6 binary zeros followed by a 1 is equivalent to 129 in decimal. Using our language analogy, this is French, this is English. Different language, but we're saying the same thing. Using Windows Calculator once again, 129 in decimal is equivalent to 1 followed by 6 zeros and a 1 in binary. Tomato, tomato. What about 16? So 16 equals 16. This is an easy one. This bit is the equivalent of 16. So that bit is set on. The other bits are off. So 000, 1, quadruple 0 in binary is equivalent to 16 in decimal. And lastly, 123. 64 plus 32 plus 16 plus 8 plus 2 plus 1 equals 123. In other words, the first bit is off, second bit is on, which equals 64, third bit is on, 32, fourth bit is on, 16, fifth bit is on, which is 8, seventh bit is on, which is 2, and last bit is on, which is 1. So 64, 32, 16, 8 plus 2 plus 1 gives us 123. In other words, 0 followed by 4 ones, followed by a 0, followed by 2 ones in binary is equivalent to 123 in decimal. Just to reiterate, remember 2 to the power of 0 equals 1 in decimal, 2 to the power of 1 equals 2 in decimal, 2 to the power of 3 is 8 in decimal, 2 to the power of 4 is 16 in decimal, 2 to the power of 5 is 32, 2 to the power of 6 is 64, 64, 32, 16, 8, 2 and 1 equals 123, so the most significant bit is set off, second, third, fourth and fifth bits are set on, the sixth bit is set off, the seventh and eighth bit is set on. That gives us this value in binary, which is equivalent to 123 in decimal. I'm hoping that shows you how to convert a decimal IP address into binary. Now let's do it in reverse, binary to decimal. So in this example, if we were given this IP address in binary notation, how would we convert that to decimal? So using our table, the first bit is set on. So that is equivalent to 128. Second bit is off. Third bit is on. Fourth bit is off. Fifth bit is on. Sixth bit is on. The last two bits are set off. So first bit is 128. 64 is not used. Third bit is 32. Fourth bit is not used. Fifth bit is 8. Sixth bit is 4. And the last two bits are not used. That gives us 128 plus 32 plus 8 plus 4, which equals 172. So 10101100 in binary equals 172 in decimal. Looking at the second octet, we have 3 zeros followed by 1, followed by 4 binary zeros. So in our table, the fourth bit is set on, the other bits are set off, so this is the equivalent of 16. So 0001 followed by 4 binary zeros is equivalent to 16 in decimal. By the same token, the third octet, filled with zeros except for the last bit, that is equivalent to 1 in decimal. Or if we populate the octet with ones, that is the equivalent of 255. So that's an example of doing binary to decimal conversion. That concludes this HP Expert 1 video explaining binary. In this video, I explained the basics of binary. I showed you how to convert a decimal value into binary and how to convert a binary value into decimal. I also extended that to the conversion of IP addresses. Thank you for watching. For more information, please visit hp.com/go/expert1.